I'm Brendan, and this is the binary pattern generator, and it's a project I did when I was a graduate student in Parsons, and the design of it I've been working on ever since for the past 3 years, refining it and creating different versions of it. But this was the first version, and so I'm just going to tell you about the system that it operates on and the individual functions of each modules. So it looks like a Eurorack, which is a popular analog synthesis platform where you can purchase modules from different developers and designers, and then because they're all set on a similar set of standards, they're able to intercommunicate with one another. Now I just only use the format. These aren't Eurorack compatible modules, and in fact they use banana cables. These are single conductors, and they're unlike the 1/8 inch conductors that a Eurorack system uses. So also different from the Eurorack format is that this isn't actually a synthesizer. It can be used to generate music, but it's not doing any kind of analog synthesis. What it's doing is kind of operating as a programmable player piano, and the piano part being your computer. So we program the sounds that we want to make using the modules, and then this sends out MIDI information through the cable that plays the synthesizer contained in your computer. So just to demonstrate very quickly, over here, this is where all the signals start. You can't make any sound without using this module first. And I've given them all kind of funny names. So this is time generator, and this is 40-40-40, splitter, shove plus plus, destiny clock, and the congregator. So everything starts with the time generator, and your output module, the thing that interfaces the rest of the system with your computer, is the congregator. So we can start over here with one output from the time generator and plug it in over here. And every time the light turns on, we've got a note playing, and I've got it connected to a synthesizer in Ableton Live. And because we're working with MIDI information, we can use any kind of sound we want. So we let the computer do all the synthesis, and we, when using the binary pattern generator, only focus on the composition. So this is just the simplest thing you could do, but we'll get more complex from there. This is the time generator, and it's got 10 outputs on it, and they're broken into 2 parts. So these 5 knobs over here output to these 5 jacks, and this is the faster speed. You can see that these are blinking at a much faster rate. This is as low as it can go. That's the slowest this channel can blink on. And then these 5 knobs over here are paired to these 5 jacks, with each knob and jack being a set, and these operate on a much slower frequency. So this is the slowest that can go. So you get 10 outputs, and they're set to 2 different ranges that they can cover. So if you want to use a lot of the modules, they rely on breaking down the signal that you're putting into them, dividing them. There's no multiplication. The signal doesn't get faster, it only gets slower. So you kind of get a cascading effect with the modules that you're connecting. So starting with a faster signal, if that's what you want to do, we're going to start with this one up here, and the top left knob controls that. We're going to plug it into the 40-40-40, which is actually the same module 2 times contained within one. So the white jacks, for the most part, are the inputs, gray jacks are all outputs, and black jacks, in this instance over here, could be inputs or outputs. So we've got the white jack up here. This is a module that only takes 1 input. So I plugged in the clock speed into the time, and what the 40-40 does is divide the rate of this blinking light by half with each of its steps. So it might be difficult to see up here because these are flashing relatively quickly, but if we look down at these channels, we can see that this light is blinking at twice the rate of this light. And so we've got basically a harmonic breakout octaving, if that's a word, octaving, of the signal. And using these 12 outputs, we can connect to other modules, or we could just plug these in straight to the congregator. And this is a fast way to get some sounds. So it's not sounding that great, but that's okay. Just get a little interesting. There's also one more output on the 4040 that has a question mark on it, and that question mark is linked to, at any given point, linked to one of these 12 outputs, and this knob controls what it's connected to. So as I turn the knob, we can see that right now this blinking light for the question mark is actually the same as this channel, and that can add some kind of tactile engagement for the user to quickly change things that they don't like. Let me just demonstrate that. Alright, and so that's how this module works. And you get two of them, which means you could plug two different clock signals into them, or divide a clock signal coming out from one module to the other one, and you can get kind of the in-between steps between frequencies. But right now we're going to plug the question mark out of the first 4040 into the shove plus plus. And it's called shove plus plus because it's a shift register. And the way a shift register works is it's expecting a clock signal and a data signal. And whenever it receives a clock signal that goes from low to high, the module checks the data line, and if the data line is a high signal, then it pushes into the first output the signal that's on the data channel. So if we go clock is happening, it goes, okay, what's happening over here? And if that's high, then it pushes this information into here. So that's why it's called a shift register. It shifts the incoming register. And the next time the clock happens, the signal that was here moves to here, and the new data comes in. So I've got this clock blinking at this rate over here. And when I plug this in, we're going to see these LEDs on the shove plus plus module advance by one step. It will kind of look like a waterfall. You can see that these are being pushed forward at the rate that this is blinking, and we can speed that up a little bit. Maybe it'd be more effective with... And you can see that the channels are filling up with empty LEDs. That's because we don't have any signal coming into the data. But let's get this one in there. Also make it a little faster. You can see how there's kind of like this waterfall happening. And the way these steps goes, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. And over here we have right now these two inputs are controlling these 16 outputs, but we can have these two inputs just control these 8 outputs, and then these two inputs control these 8 outputs, and we do that by switching this switch. And so now the data and the time on the left-hand side are only controlling the left-hand side of the module. But if we set it up, it will control both sides. The other side is controlled the same way the left side is, but we can add a different clock signal there. So now we've got one side running off of 2 different signals and the other running off of 2 different signals as well. Plug it in. So that's kind of how the shift register works. We're going to use the shift register for the next module, and we're going to set it so that these two are controlling both channels. Let's get something that looks nice. I like the way this looks. So the Destiny clock is really the most exciting part of the whole system. It takes, we're going to use it for an example where we have one incoming signal, and then that signal can get routed to any one of these 8 outputs. And the way it gets routed to any of the 8 outputs is by using 3 input selection signals. If you want to think of it where this is +1, +2, and +3, and these can be combined in different ways, then this would be 0, 1, 2, 3, 4, 5, 6, 7, all the possible outputs. So right now if none of these are on, we're adding basically 0, so we'll plug a signal into here, and it will come out of here, because we're not adjusting it with the input selectors. So here I'll show you how this works. We're going to do +1 over here, so when I do +1 it's going to move to there. That's what +1 looks like. And then the next is +2, and that's how it moves to there. And you can see that by forming a combination of +1 and +2, we can get all the way up to 3. And then the last thing is +3, and that would do 0, 1, 2, 3. Sorry, this is +4. +1, +2, +4. So when I turn this on, it will go here, and then we're at 4. Now it's at 5, and then this would be 7. And then if I had one more cable, we could make it go up to 8. And so the really exciting thing about this module is that you're not going to be, plugging in these static signals. You're going to be plugging in signals that are changing. And one of the most exciting things from like a computer science digital electronics perspective is that we can have this module count sequentially based on the output of the 4040 clock divider. So we'll take the first input, or we'll take the fastest frequency we're going to use. That's still a harmonic of the original frequency, and that is almost, there we go. We've got that going, and then we're going to take the next division and plug it into the +2, and so we can see it's already counting sequentially a little bit. And the next one will be the next division, and now we're counting through the steps like that. And that looks a lot like a step sequencer. So you might as well plug the rest of them in. Alright, so the question mark output that I mentioned over here is really great for feeding into the Destiny clock. So I'm going to take the +1 signal that I have connected to this frequency and exchange it for the mystery clock signal, and now I can jump through steps to change the way the sequence functions. Right now we're only going through 4 notes, and that's because the signal coming out of the question mark is the same signal that's going. These are the same. +1 and +2 are the same. And we'll keep going through this until we find something we like. And as we get slower frequencies coming out of the question mark output, we're getting something that sounds more like a musical composition.
So question mark is feeding which input of the Destiny clock?
The first one right now.
So the +1.
Yep.
Okay. And then what's feeding the input, sampler input? The I/O or on/off?
This is just a static signal that's hanging out over here.
So when that divides to be... Oh, I see, it's on because you don't have anything going into the 40-40-40, so it's just going to stay on.
That's kind of a downside of this design, is that there's no way to just get an on signal. You kind of have to sneak them out of other modules that aren't in use at the time. But we could also take that signal, the on signal, and plug it into something like this. So now it's firing at twice the rate. We could also, if we wanted to play a note, the fastest frequency on this one, if we plug the fastest frequency, this input output into the fastest frequency, which is this one, we're going to use the splitter module to combine them together. It'll sound... Not what I was looking for. Well, I think this is what I was going for. I'd kind of like to make it faster though. That way we get two notes firing. And then we could get 4 if we go even lower over here. So this one's quite fun. There's also a second one down here, and you can actually feed the signals from this one into this one, and that will give you two kind of step sequencers that are interlocked with one another and will release notes in like a pretty good sounding way. So that's kind of how everything functions, and I don't think I have too many tricks to show and tell with it, but there you go.
Excellent. Thanks for the demonstration.
No problem.
Do you mind turning up just a little bit and we'll just record a little bit?
It's funny how it makes those like...
I know, that's why I love it.
I'm not sure what that is.
Just more excited electrons. So Brendan, can you explain how you did this alternate patching of the Destiny clock?
Sure. Kind of. I'm using both clock dividers, with this clock divider feeding into the one on the right with the mystery output. So as I change this speed, this signal gets sent over here. So let's just change that. The slower it gets. You can see that. These are synced together. And this one is controlling primarily the bottom. These signals coming out go to the Destiny clock on the bottom. And in the example I showed before, we were using the module as receiving one input and it being routed to 8 outputs. Well, in this case, I've got 4 inputs and they're being routed out through a single output, and we've got 2 selection bits, so that's why we've only got the top 4 and not the bottom 4. And the output is being fed into the input of the top module, so that as these lights blink at different rates, it will trigger these notes in a different rhythm depending on which one of these channels is selected as the output to go to the input of the other one. These selection bits over here are being controlled by the slower clock on the right. Yeah.
So the least significant bit and the next most significant bit are receiving these slower patterns.
Yes.
Okay.
I'm trying to think of something. Oh, we can let's take the output from the bottom module and plug it into a selection bit at the top, and then we'll have a straight signal go into the input at the top.
Yes.
So that's pretty cool.
Very cool.
Mm-hmm.
Do you want to describe this patch?
Yeah, sure. So, similar setup to before, using the second Destiny clock down here. We've got 4 different clock rates coming into it, and one output that's determined by 2 selection bits coming into it. That output is being used to control the data input on the shift register, and so because the data is changing in length while the clock remains steady, we get the same tempo we would expect, except that the data bits that are coming in are at kind of infrequent intervals, like some bits are longer than others, and that's what allows the kind of like irregular kind of display that's going on here. And so because we've got the first selection bit on the second Destiny clock hooked up to the division selector up here on the first 4040, we can change the kind of sound we get from the whole thing. And one thing we haven't tried yet is the time coming in is steady, but let's see what happens when we switch the time and the data. So now the timing interval will be different. this steady.